So hello everyone, my name is Fabio Diaz. I'm a postdoc research at the University of Helsinki, and today I'll talk about this work that was actually developed at the University of Tasmania during my PhD, where you investigate this subpolar Southern Ocean response to changes in the surface, momentum, heat, and freshwater fluxes under a double CO2 scenario. So the Antarctic subpolar Southern Ocean has a great climate importance, mostly because it's a region of formation of the global densest water mass, which is the Antarctic Bottom Water, which feeds the lower limb of the Meridional Overturning Circulation, and then it's essential for the recirculation of heat, salt, and carbon throughout the global oceans. And it actually fills around 36% of the global ocean volume. So the formation of Antarctic bottom water depends a lot on very small scale process at the continental shelf, such as coastal polynyas associated with katabatic winds in some regions, and the mixing of local water masses in the continental shelf, including meltwater from the ice sheets, and also the downslope sinking of the Antarctic bottom water from the continental shelf to the deep ocean. And actually, global climate models struggles a lot to represent these mechanisms because of their resolution, and also due to uncertainties in the surface fluxes. So usually those models show large open ocean polynyas, especially in the Weddell and Ross gyres, that usually form too much and too cold Antarctic bottom water. And although these events of open ocean polynyas has been observed in the past, it is quite rare, which has been only observed twice in almost 50 years. So our goal here is to understand how the Antarctic bottom water and the subpolar Southern Ocean responded to change associated with anthropogenic induced climate change, and which is essential for the projections of the sea level rise, mostly to the effects of the melting of the Antarctic ice sheets, but also due to the thermospheric sea level at the deep ocean. So to investigate the subpolar Southern Ocean response to individual perturbations of momentum or winds, heat, and freshwater fluxes from double CO2 scenarios, we use an coarse resolution global ocean sea ice coupled model, the ACCESS OM2, and you perturb this model with surface fluxes from the flux anomaly forced model intercomparison project, which you can see on this figure, the surface flux perturbations, and which is basically at the Southern Ocean, you see this very intense strengthening and poleward shift of the winds, but also positive heat and freshwater fluxes. So jump to the results, we have seen that the wind changes in the FAF stress, well, how do you call these experiments? It causes intense cooling throughout the subpolar Southern Ocean, as you see in the subplot A here. And also in the plot B, you see that this cooling goes throughout the water column as well. And this response to the wind perturbations is exactly the opposite that we observed in the heat and freshwater perturbations, so the FAFA heat and FAFA water experiments, which induced a warming response. So when you apply all these perturbations combined in the FAFA all experiment, we see that it's actually dominated by the wind effect, which was quite a surprise. As you see here, there's cooling in the subpolar Southern Ocean, mostly happening at the Weddell gyre and in the Ross Sea region. But this cooling in FAFA all and also in FAFA stress, it actually has a quite strong time variability, as you're gonna see further. So the response to the wind changes, it's associated with change in the sea ice coverage and also the mixed layer depths, where you can see that in fafa stress there's a strong deepening of the mixed layer and a quite significant reduction of the sea ice concentration. Okay, you see this in the plot C and D here. And when you compare that with the FAFA heat and FAFA water experiment, you see exactly the opposite effect. You see that the mixed layers actually get shallower due to the heat and freshwater perturbations, and the sea ice concentration increases. And this deepening of the mixed layer and reduction of the sea ice concentrations is associated with open ocean polynyas in, of course, FAFA stress and FAFA all, and that seems to affect quite significantly the abyssal meridional overturning circulation. So there is this very strong increase in the MOC transport, which also has a quite strong time variability. And when you compare the time series of the meridional overturning circulation with the ocean heat content integrated in cross sections at the Weddell and the Ross gyres, we see that occurs in parallel with decreasing of the ocean heat content. And then we also look at how that's associated with the sea ice tendencies, or in the sea ice budget, and it shows that the timing of this decrease of ocean heat content and increase of the MOC is associated with very strong decrease in the thermodynamic sea ice growth during winter time in both regions. And you also look at the same cross sections in the Weddell and Ross gyres. You look how the temperature profile evolves. So you did some half-molar plots, and you could see that in the experiments where we observe increase in the open ocean polynyas, there's a strong deep cooling associated with deep convection during the open ocean polynya events, while the FAFA heat and FAFA water experiment shows a quite intense stratification of the water column. So basically this leads us to conclude that the deep convection events require some heat storage at depth, and the deep convection is maintained while we still have heat to feed this mechanism. But when this heat is depleted at depth, it terminates the event and starts to building up heat at depth again. And here you show some snapshots of the sea ice budget, where you decompose the total volume ice thickness into a thermodynamic and a dynamic plus transport components. And you can see here that so in the first column is the average throughout 10 years, which doesn't have the polynya in the control run, and in the column in the middle you show a snapshot for one event in the Weddell Sea, and in the right column is a snapshot for one event in the Ross Sea. So basically, you could see that in both regions, what drives a decrease in the ice tendency is actually this decrease in the thermodynamic ice growth, and that happens actually within the open ocean polynya. And that indicates that you have upwelling of deep warm water that helps to melt the sea ice or decrease the thermodynamic ice growth. And that's the trigger of the open ocean polynya that's gonna cause deep cooling and deep convection events. And when we look at the surface heat fluxes, we could see that the experiments that show open ocean polynyas or increase in open ocean polynyas, there is quite an increase in the surface heat loss, and that causes more Antarctic bottom water formation through cooling. So at open oceans, the temperatures and the diagrams show that the bottom water becomes more colder, but it also, when you look at the continental shelf, it also shows that it's also more salty. So it indicates that also there is a role of coastal polynyas and high saline shelf water, which should become more frequent when you have these changes in the wind forcing. And basically our results, so just to summarize it, there's this strong correlation of the change in the wind forcing, so basically the strengthening and the poleward shift of the westerlies. It causes ocean cooling and excessive Antarctic bottom water formation, and that's only partially compensated by the effect of the heat and freshwater fluxes, which cause increase in stratification and decrease of these open ocean polynyas and deep convection events. And this result suggests that convective models such as the XSLM, they tend to respond to double CO2 scenarios with abyssal MOC acceleration and abyssal cooling associated with more Antarctic bottom water formation in those open ocean polynya events. But it may indicate also that model that doesn't have those open ocean polynyas so often or doesn't form it, they may have a totally opposite response. And you suspect that is quite a great contribution to the thermostatic sea level projection. So the formation of Antarctic bottom water is well known to be a quite deficient aspect of global climate models. And we show here that the response of the subpolar Southern Ocean to changes in the surface fluxes can be associated with actually cooling and intensification of Antarctic bottom water formation, but due to the wrong representation of Antarctic water formation process. So that's something that you should look more carefully when you analyze sea level projections from climate models. That's all. Thank you.